Hello everyone and welcome to solutions video for educational round 118. So let's get started. Problem A, long comparison. So in this problem we are given four numbers x1, p1, x2, p2, and what these pair of numbers evaluate to is an integer. Like, so let's say x1 is 137 and p1 is 5, then this evaluates to 137 and then 5 zeros. Let's say x2 is 72 and p2 is 6, so this evaluates to 72 and then 6 zeros. What we want to do is give the comparison between the evaluation of this pair and evaluation of this pair. So to do this, first of all, notice that the overall length of whichever number is greater will be greater, right? No problem there. So the first thing we need to do is, okay, let me zoom. So the first thing we need to do is calculate the length 1 and length 2, which is, we first of all convert the integer to a string and then get the size and then the number of zeros, which is p1. Similarly L2, and if L1 is greater than L2, we say pair 1 is greater. Otherwise if L2 is greater than L1, pair 2 is smaller. Now, however, if both have same number of digits, then what we want to do is as in this case, you can see, right, there are 8 digits here and 8 digits here. So we want to evaluate which one of them is bigger or smaller or equal. So we have to take the first 3 digits to evaluate. We cannot evaluate based on the first 2 digits, because what if it was like 7, 2 and then 7. So if we evaluate based on the first 2 digits, we'll get equal. We want to evaluate based on first 3 digits. So to do this, what I'm doing is, as long as the length of the first number x1 is less than the length of the second number, I multiply it by 10, because we know that these two numbers are equal. So I can just pad zeros on the right side of the smaller one. That's what I'm doing here. So here the number was, okay, let's go to the original number. So here the number was 137, here it was 72. I pad zeros on the right of the smaller one in terms of length. So I add a 0 here and then I do the less than, greater than, or equal to comparison, as you can see here. So a pretty simple implementational problem, I would say. Now the second problem, absent remainder. So in this problem, okay, let me use black. We are given an array where all numbers are unique and we want to find n by 2. So this is the floor division. So n by 2 pairs of number such that n by 2 pair of numbers x comma y, such that x and y both belong to this array and x modulo y, let's say it is z does not belong to the array A. So we want to find such n by 2 pairs. Now notice that, let's say I chose some x and y which belong in this array, and if x is less than y, right, then x modulo y would be x, which does belong in the array, right, because okay, which does belong to the array because x belonged to the array. However, if x was greater than y, then x modulo y would be less than y, which may or may not belong to A. So how can I guarantee that this does not belong to A? That's right, choose the smallest y. So if I choose the smallest y possible, which is, let's say this is the sorted version of the same array, Then if I choose y equals to b1, then any number I get will be smaller than b1, hence not equal to any of this array, any of the number in this array. So if I take y equals to b1 and x equals to anything b2, anything from b2 to bn, then I can get a valid pair. And remember, there is no such condition that their remainders cannot be equal. They can be equal, in case you misread the problem like me. So yes, so you just have to take n by 2 numbers from here and choose y always to be b1, and you will be guaranteed to get the n by 2 pairs which satisfy the condition. Implementation is again trivial, you can see here. So integer n, I take the input, I sort the array, and then I go from 1 to n by 2 plus 1 because I'm taking the 0th element for the y value. So this is the y value, this is the x value. Okay, so third problem, poison dagger. So what this problem says is that we are given n values, we're always given n values. So and these values are like on a number line. Okay, so I have a1, a2, a3, a4 and an. And so there is a dragon, we are attempting to kill it, and we will make these n strikes at these n moments of time. Okay, this is time axis, it's not a unitless number line, it is time axis. So we make a strike at point a1, then we make a strike at point a2, make a strike at point a3, and so on. And every time we make a strike, what happens is the dragon gets infected by poison, which causes the dragon to take damage for k seconds. So if I hit him here at a1, he would take damage for k seconds. So a1, a2, a3 up to, so this last second where it would take damage would be the a1 plus k minus 1th second. Okay, now in this case, let's say k was this much. So what happens is this poison effect will only go on until a4 minus 1, and then a new poison effect will start from a4 because a new strike happened, and it will go till a4 plus k minus 1. And so yeah, this keeps happening. What we want to tell is we want to tell the minimum possible k such that the dragon can be killed, and dragon can be killed if the damage done is greater than equals to h. So notice, if I can kill the dragon using some k equals to k, then I can definitely kill the dragon using k equals to k plus 1. So it is like, so let's say the range for value k is 0, 1, 2, no, 0 is just impossible, let's not care about it. So 1, 2, 3 up to, let's say, h, the health of the dragon. So if I can kill, and let's say there is some x, if I can kill him using x value k, then x plus 1 is also sufficient, x plus 2 is also sufficient. These may or may not be sufficient. So it is like I cannot. Okay, so I cannot kill it using 1k, not using 2k either, not using 3, but maybe at some x I can be able to defeat it, and so on, right? So anything, so it is like this, right? And this is a classic case of binary search. I can binary search on this range. If I am able to kill it using, let's say my mid value is this, then that means I'll be able to do it using anything more than that value. So I will search in the smaller range. which is this range, and then I will do the binary search again. For a little bit clearer understanding, let's do it again. Let's do a little bit of dry run. So these are the possible values. H is 8. Okay, so these are the possible values. Let's say I try with 4. So if I try with 4 and I'm unable to kill it, then that means I won't be able to kill it using these either. So I have to search in this space now. I try with 6. Let's say I'm able to do it. So that means I'll be able to do from 6, 7, 8, all of them. So search space reduces to this. Now I will check here if I can. Good, this is the answer. Otherwise, this is the answer. So classic case of binary searching on the answer. So I take in the input and I append an infinity at the end of the value a, and there is a reason for that. Sorry, the array a, and it is just for a cleaner implementation. I'll tell you why. So initially answer is 0. I binary search in this range 1 to h. I get the mid value, and then I calculate what is the maximum damage possible. That would be, so if you see this number line, it is either the damage done is this k, right, or it is this value a4 minus a3, right? So I take the minimum of either this or whatever value I'm checking, which is mid, and as you can see, since I'm checking with from the first index and not the 0th index, so when there's only one point, I will need to, for the last point, sorry, so let's say using this implementation, right, when I'm at an, there's some an minus 1, so I calculate the damage done by an minus 1 its attack. But what about the nth attack? I'll have to do it separately. So instead of doing that separately, I just add an infinity, so that this damage always comes to be mid. And then if the sum is greater than equals to h, answer is equals to mid, search space goes from low to mid minus 1. Otherwise, search space goes from mid plus 1 to high. And this line is there just to avoid any overflows. It wasn't really possible, I think, but whatever. So problem D, the actually tough problem. Okay, how do I explain this? So first of all, let's see what MEX correct means. If you misread this, you will end up wasting at least half an hour like me. So what MEX correct means is, let's say we have a sequence x1, x2, x3, xk. Then what I want for all I is that the MEX of x1, x2 up to xi to be either xi plus 1 or xi minus 1. So what MEX is, MEX of a set of numbers, right? 1, 2, 4, 0 is the smallest non-negative integer that does not occur in them. So 0 occurs, 1 occurs, 2 occurs, 3 doesn't occur. So 3 is the MEX. So I just want the MEX at every step of the array, the prefix MEX of every step of the array, to be either equals to xi plus 1 or minus 1, because they had asked us the absolute difference to be less than equals to 1. But as you know, if I have xi in the set, MEX cannot be xi. So MEX must be either xi plus 1 or xi minus 1. Okay. So now that we have the proper definition in our mind, let's try to solve it. Okay, so what we want to do is, we are given an array just like normal, A2, 3 up to AN, and we want to find the number of subsequences which are MEX correct and print it modulo this value. So no, so there are two type of, so at any, for a subsequence, like I mentioned, the MEX at every step should be either xi minus 1 or xi plus 1. So the two type of MEX are, so type 0, that 0, 1, 2, some I value is covered, and then sorry, some I minus 1 value is covered, sorry, some k, okay, let's use k, some k minus 1 value is covered, and this kth value is not covered. So whatever I'm doing in this bracket means is in the prefix array. So there's this one type of MEX we get, right? In this case, the last value has to be x minus 1 and the MEX is k. Sorry, k minus 1 and the MEX is k. And there's this type 1 where values like up to k minus 1 is covered. The k is the MEX, okay, and k plus 1 is the value at ith index, okay, or k, or value at k minus 1 index. Sorry. So these are the values that are in the set of prefix of the subsequence, and the last value can be either k minus 1 or k plus 1. Now if you look at this, you will notice that there is a lot of interchangeability. That is, if I add a number k plus 1 to this set, I get this form. Wait, if I add k plus 1 to this subsequences of this type, I get this form. And if I add a number k to this type of set, right, I get, so this whole will be covered and I will get of type this. So as you can see, there is a lot of shared counting in between them, and that gives a hint to DP. That's right, this is a DP problem. So let's okay, I will put them in a space like this. Okay, so 0, so type 0 is like this, and type 1 is like this. And now we wanna see how the DP will be. Okay, I thought I would draw much better. So I have A1, A2, A3, A4, A5, AN. So at some I, let's say A4. So for now, let's store the minimal state. As we can see, there are two types of states. So for every I will have two type of values. So this will give me DP I0 and DP I1. DP I0 would represent the number of subsequences that end at I and are of type 0, and DPI1 would represent the number of subsequences that end at I and here I is this index, okay, at that end at I and are of type 1. So now that we know our state, let's write that down as well before proceeding. So I have state as well, which is DP I 0 and 1. Okay, So this is my state. Now let's have a look at transition. So let's see how can we form dpi0. Okay, so dpi0 will be formed. First of all, let's say ai is equals to x. Okay, so dpi0 will be formed from values of type 0 and 1 both, right? So it will be formed, but the constraint there is that their ending value should be very near to x, right? It can be x minus 1, x, or x plus 1, something like that. Not not formally correct, but it cannot be more than that, because otherwise this condition will get false, and it won't be a MEX correct array. So that means that instead of our initial, okay, I didn't even say that. So dpi0, if we were to do it in a more brute force manner, okay, if we were to do it in a more brute force manner, what we would do, dpi0 is formed using, okay, so is some sort of concatenation. Okay, I'll use sigma here, but it is not summation exactly. Okay, so it is some sort of concatenation for all dp j 0 and 1. Okay, so v and j is from 0 to I. So just like in longest increasing subsequence dp, since our dp state is pretty similar to that, and we want to form subsequences, it makes sense that dpi will be formed from dpj, right, where j are less than I. And now but this is not possible, right? So this type of transition is not possible for us. So whatever this function is, right, it is not possible for us because we cannot iterate through all j. This would become n square, and that's where this observation comes in play. The observation being that this only affects some portion of the final count dp, and that is only the neighborhood of x. Okay, since it's only affecting the neighborhood, that means of all the j, we only care about where aj belongs to okay, so we only care about j that belongs to x, x minus 1, x plus 1. Okay, the neighborhood of x. So due to this we don't actually have to iterate through all of the previous j, right? Instead, what we can do is we can store them in a final dp array, or whatever you can call the array. So in the final container, this is our final container. Okay, which, so initially we were thinking like dpi0 represents for ith index and 0 type, I1 ith index first type, but now let's make which represents 0, 1 up to n, and this represents the MEX with 0 type. Okay, I don't know if it was possible to follow this one, but let's see. So our dp is now x0i. It doesn't represent the index, it represents the MEX value. Okay, so what dpx means is the number of subsequences that end with MEX is equals to X and index end of type 0 or type 1. Okay, so TLDR of all that mess was that we were thinking of doing in index. Okay, we were thinking of doing in index, but we saw that if we were to store DP in with index as the state, then we will have to iterate through all the previous indices, and that is a mess. However, since only the previous indices that whose value is in the neighborhood matters, and we can just update it, we will try to use a DP like this, where X is the final max and 0 is the type of 0 and 1 depicts the type. And now let's have a look at our transition. Okay, so let's update that and have a look. So this is X, and let's have a look at the transition. Okay, let me draw a red line. So the transition, so type 0 is like this, right? And type 1 is like this. So if I were to put my, so we will iterate through all the indices, right? And let's say I'm at the ith index and AI is equals to X. Okay, so let's say now this value X, now I can put it either here or here or here or here or here or here. So because only if I put it somewhere else, let me show you. Okay, so why I cannot put it anywhere else? Because if I were to put it somewhere else, okay, let's say I put it here, then whatever the max would be, let's say max would be around here, the difference between them would be greater than 1. So since we want the difference to be within the range of 1, the absolute difference, the current range of where we can put X is this much. It won't be this much either, something will get eliminated, but let's move on. Okay, now I'll use blue. Okay, so I have 3 positions, right? This position, this position, this position, this position, this position, and this position. So if I were to put X, at this position, okay, for on 0 type subsequences, so what I'm doing is I'm putting my new value AI, that is X, into some of the previous subsequences to see if I'm able to form another MEX correct subsequence. So here, let's say I've put X here. Okay, if I put X here, the MEX remains this value. Okay, so in case you forgot, this is the MEX. This is the MEX. So if I put X here, the MEX remains X plus 1, right? And but just so which all the subsequences which had max X plus 1 and were of type 0, they got doubled, right? Because now for all of them I can put another X and the max would still remain X plus 1 and all the conditions still meet. And if I were to put it, let's say here, okay, if I were to put it here, then and see, I'm saying I'm putting it here or here, but actually I'm moving the subsequences, sorry, the MEX correct sequences, because X is fixed. Okay, so if it were to be placed around here, then what happens? All of this gets covered, right? And DP. Now again, adding this would again add to the MEX would become this, right? But x plus 1 is this now, since x is this. So x plus 1 of type 0 gets incremented by this value. Why? Because the number of subsequences which had MEX x, right? Sorry, MEX x. In them I'm adding x at the last value and getting x plus 1 MEX. If I were to put it here, okay, if I were to put x here, let me erase first. Green. If I were to put x here, what will I get? As you can see, let me use the eraser again. As you can see, I have these values covered and this value covered, which is of type this, but max remains x. So dp x of type 1, this got incremented by dp of max of type x0, right? When max was x, but it was of type 0 and I added here, it became of this type. Now let's add here, okay? If I add here, the max remains same and everything remains same. Max was x plus 1 in that case. This just got multiplied by 2. If I add here, okay, if I add here, it becomes of type 0 where max is this, but the difference becomes 2. So I cannot add here. So yeah, I cannot add here. And if I add here, then as you can see, it still remains of the type, it still remains the same, but this time it is of max x minus 1. So these are the transitions, and let's have a look at the implementation. It is possible I might have overcomplicated it. Okay, so I have vector. I stored the frequency. This was not necessary. This is the DP. And here gonna be some implementational details. So first of all, I get X as AI. So that's why I use the same nomenclature here so that it is not confusing. So first of all, I increment this X plus 1, 0 multiplied by equals to 2. Then, and now remember, what if this value was 0? Okay, if this value was 0, then of type 0, right, where max is 1, will also increase by 1 because I can independently use it. So this is the independent case. And then x plus 1, 0 plus equals to x0. And now I'm adding this condition just for segmentation fault so that I do not run into that. Now x minus 1, 1 multiplied by 2, as you can see. And then I have again the base case or the independent case. When I choose 1, okay, this is empty, max is 0. This is of type 1, right? And x minus 1, 1 plus equals to x minus 1, 0. And then I have this x plus 1 multiplied by equals to 2. So yeah, and as you can see here, I'm updating x minus 1. First of all, I'm multiplying it by 2 and then I'm adding the previous ones. So notice here, I cannot do it in the opposite order. Reason being the actual transition is like x minus 1, 1 plus is equals to the previous value and then x minus 1, 0. Okay, it is something like this. Now I cannot, because it was like this. I just did it separately. First of all, I multiplied by 2, then added this. But yeah, and similarly here as well, the ordering is important. And then in the end, we go through all the possible states and just add the type 0 and type 1 subsequences and then print the answer. That was it. Scuffed explanation, I think, but hopefully it was understandable. And if you liked, leave a like. If you didn't, leave a like. If you liked, subscribe.